The invention of precision agriculture is a story of quiet revolution, a remarkable transformation in the way humanity cultivates food. Yet it remains one of the most overlooked innovations in modern agricultural history. Unlike inventions that capture widespread public attention, precision agriculture has evolved gradually, blending traditional farming knowledge with breakthrough technological advancements. Its true power lies not in a single invention or moment, but in the integration of many small, interlinked innovations that have together redefined farming practices, making them more efficient, sustainable, and capable of feeding a rapidly growing global population. To understand the profound impact of precision agriculture on the modern world, we need to explore the journey of its development from its earliest origins to the sophisticated technologies that now allow farmers to cultivate their fields with unprecedented accuracy and care, and examine how these advances have reshaped global food production and sustainable farming systems. For much of human history, agriculture was guided by intuition, inherited wisdom, and observation of natural patterns. Farmers relied on sensory information, touching the soil, observing crop color and growth, noting weather conditions, to decide when and how much to plant, irrigate, fertilize, and harvest. This method, though time-tested, treated agricultural land as largely uniform, overlooking the subtle variations in soil nutrients, moisture content, and microclimates that could drastically affect crop performance. The consequences were often inefficiencies, excessive use of water, fertilizers, and pesticides, wasted labor and resources, and sometimes lower yields. These inefficiencies became increasingly problematic as global population growth and food demand intensified, pushing traditional farming methods to their limits and highlighting the need for more precise, data-driven approaches. The first seeds of precision agriculture were planted in the mid-20th century, catalyzed by the emergence of new scientific tools and technologies. In the 1950s and 60s, advances in remote sensing technology enabled researchers to use aerial photography and satellite imagery to observe fields from above. These images unveiled patterns of crop health and soil variability invisible to the naked eye. Scientists could identify areas suffering from nutrient deficiencies or pest infestations, providing valuable clues for targeted interventions. This marked a turning point, signaling the potential to move from broad, uniform treatment of fields to site-specific management. But practical application was limited by the lack of precise location data and real-time analytics. The breakthrough came with the development of the Global Positioning System, GPS, in the 1970s and 80s. A technology initially developed for military navigation, GPS allowed for accurate determination of geographic locations anywhere on the planet. By the 1990s, the availability of GPS for civilian use revolutionized agriculture, enabling farmers to map their fields with unprecedented spatial precision. Coupled with geographic information systems, GIS, farmers could overlay soil maps, topographic data, and yield records to understand exactly which parts of their fields required specific attention. This spatial awareness formed the backbone of precision agriculture. Alongside GPS and GIS, variable rate technology, VRT, emerged as a key tool. VRT allowed farm machinery to adjust the application rates of seeds, fertilizers, and chemicals dynamically as they moved through different parts of a field. Instead of blanket spraying or fertilizing entire fields uniformly, inputs could be precisely calibrated to soil and crop needs in each microzone, reducing waste and environmental impact while maximizing crop performance. This precision reduced input costs for farmers and lessened the ecological footprint of agriculture, helping mitigate problems such as nutrient runoff, soil degradation, and groundwater contamination. The 21st century brought a rapid expansion of sensors and digital technologies, accelerating the evolution of precision agriculture. The rise of the Internet of Things, IoT, and wireless sensor networks meant that farms could be equipped with devices to continuously monitor soil moisture, temperature, pH levels, and nutrient content in real time. Soil probes, weather stations, and plant health monitors provided a constant stream of data that farmers and agronomists could analyze to optimize irrigation schedules, fertilization plans, and pest control measures. This real-time monitoring ensured resources were used only when and where they were needed, further improving efficiency and reducing environmental harm. Drones, or unmanned aerial vehicles, UAVists, became another transformative technology. Equipped with multispectral, hyperspectral, and thermal cameras, drones could fly over large agricultural areas to collect detailed images revealing crop stress, disease outbreaks, weed infestations, and soil variability. Unlike traditional satellite imagery, drones offered higher resolution data that could be gathered on demand and in any weather conditions. This capability allowed for timely interventions, preventing minor issues from becoming catastrophic failures. Complementing the hardware advances, artificial intelligence, AI, and machine learning technologies provided powerful tools to analyze the vast amounts of data collected from fields, sensors, drones, and satellites. AI algorithms could detect patterns and make predictive models to forecast pest outbreaks, disease progression, and crop yields with high accuracy. Machine learning helped optimize planting dates, irrigation timings, and input combinations based on historical and real-time data, assisting farmers in making better-informed decisions. These technologies transformed farming from reactive to proactive management. Despite these advances, precision agriculture remained relatively unknown to the general public. Its innovations were largely confined within the farming community and scientific research circles. However, its impact on global food systems has been immense. Precision agriculture has helped meet the growing food demand driven by population growth, urbanization, and changing diets. The United Nations estimates that the global population will reach nearly 10 billion by 2050, requiring a roughly 70% increase in food production compared to early 21st century levels. Since expanding farmland is limited by environmental and social constraints, including deforestation, biodiversity loss, and land degradation, increasing productivity on existing agricultural land is critical. Precision agriculture offers a sustainable solution by enhancing yields while minimizing the environmental footprint. The environmental benefits of precision agriculture extend beyond efficient input use. By reducing excessive fertilizer and pesticide applications, it curbs nutrient runoff into rivers and lakes, preventing harmful algal blooms and water pollution. Precise irrigation techniques conserve water in water-scarce regions, combating aquifer depletion and salinization. Reduced soil compaction and erosion result from optimized machinery operations and conservation tillage practices integrated within precision systems. These outcomes help maintain soil health and fertility, critical for long-term agricultural productivity. Moreover, precision agriculture contributes to mitigating climate change by lowering greenhouse gas emissions associated with farming. Efficient fertilizer application reduces nitrous oxide emissions, a potent greenhouse gas. Conservation tillage and cover cropping, often combined with precision methods, sequester carbon in soils. Additionally, optimized fuel use in machinery reduces carbon dioxide emissions. These practices align precision agriculture with global climate goals and sustainability frameworks. Economically, precision agriculture benefits farmers by increasing profitability. By applying inputs only where needed, farmers reduce unnecessary expenditures on seeds, fertilizers, and chemicals. Improved yields and reduced crop losses enhance revenues. GPS-guided machinery decreases labor and fuel costs by minimizing overlap and missed areas during field operations. The return on investment for precision technologies often justifies the initial cost, especially for larger commercial farms. Over time, these benefits have encouraged wider adoption of precision tools worldwide. However, adoption rates of precision agriculture vary considerably between regions and farm sizes. Developed countries with robust infrastructure, access to technology, and capital resources have seen higher uptake. North America and parts of Europe lead in implementation, driven by large-scale farms and government incentives. In contrast, smallholder farmers in developing countries face challenges such as limited access to technology, knowledge gaps, and financial constraints. Bridging this divide is critical for global food security and sustainability. To address these challenges, researchers, governments, and NGOs are developing affordable precision agriculture tools and training programs tailored for smallholders. Mobile phones, widely adopted even in rural areas, serve as platforms for delivering weather forecasts, pest alerts, market prices, and agronomic advice, empowering farmers with actionable information. Low-cost soil sensors and drone services are being tested and deployed to extend the benefits of precision farming to underserved communities. These efforts aim to democratize technology and enable inclusive agricultural transformation. Looking forward, precision agriculture is poised to become even more sophisticated and integrated within what is often called smart farming or digital agriculture. Autonomous tractors and robotic harvesters promise to reduce labor demands and increase operational efficiency. Advances in robotics and AI will enable machines to identify and treat individual plants with customized care, such as targeted pesticide spraying or mechanical weed removal, further minimizing chemical use. Cloud computing and 5G connectivity will facilitate seamless data sharing and decision support systems accessible to farmers anywhere in real time. Blockchain technology is also emerging as a tool to enhance transparency and traceability in agricultural supply chains. By recording data on crop production, input use, and environmental conditions in immutable ledgers, blockchain can assure consumers of food safety, ethical sourcing, and sustainability claims. This linkage between farm practices and market demands will create new incentives for precision agriculture adoption and sustainable farming. Perhaps most importantly, precision agriculture's adaptability will be crucial in a future shaped by climate change. Increasingly erratic weather patterns, rising temperatures, and emerging pests and diseases will challenge traditional farming. Precision agriculture's capacity to provide real-time monitoring, predictive analytics, and flexible management strategies will help farmers mitigate risks, maintain productivity, and protect livelihoods under these uncertain conditions. In conclusion, precision agriculture represents a fundamental but often overlooked invention that has quietly revolutionized farming around the world. It embodies the fusion of age-old agricultural wisdom with the most advanced technologies of our time, creating a new paradigm of food production that is smarter, more efficient, and more sustainable. Through innovations like GPS mapping, variable rate technology, IoT sensors, drones, and artificial intelligence, farmers today can manage their land with unprecedented accuracy and care, reducing waste, conserving resources, and increasing yields. As the global community faces mounting challenges of feeding a growing population while preserving the planet's health, precision agriculture offers a powerful solution, one that will continue to evolve and expand in reach. Its story is a testament to how incremental technological advancements, often unnoticed by the public eye, can combine to create monumental change. Appreciating this journey helps us understand the critical role precision agriculture plays in shaping the future of sustainable food systems and securing the nourishment of generations to come.